Okay, class. Let's continue. Let's continue. I know I also very tired actually since this morning until now. So, are you ready? So, you are ready? Can you please comment two? If you're ready, please comment two. Okay. Many already comment two. Yeah. So, if we look at, we maybe before we continue, we just some chatting. The what? How many of you actually staying in KL? May I know? Anyone is staying in KL or not? Anybody are staying in nearby Selangor, KL area? Maybe you can give a so that give a say give a comment 3 so that I know you are staying there. KL or Selangor area? Anyone or not? Anyone from there? No, nobody. Yeah. So you all from the from where? From Penang? Anyone from Penang or not? From Penang? Penang, Perak, we few stage that under CMCO. We got Penang, Perak, Selangor, Negeri Sembilan, is it? Yeah. Anyone or not from this few stage? Can maybe can comment 3 so that I know. Nobody. Nobody. All from where? From Johor. How many from Johor? Johor, you put J lah, so that I know how many from you. How many of you are from Johor? You just put J. Okay. J. Melaka, anyone? Melaka, quite a numbers of Melaka. M. Melaka M. Nobody. Sabah, Sarawak. Anyone from Sarawak or not? From Sarawak. Put as yes, from Sarawak, Sarawak. So I means all are yes, okay. Not Sabah. Sabah. Anyone from Sabah? Sabah, okay. Sabah, okay. So I think KL now. KL is because of the factory factory top growth, top growth. You see, Malaysia actually, Malaysia is the what the largest largest manufacturer of the growth, top growth. We have few company, big one. We got top growth contribute. I think the whole world about contributing about 20% in the world. So you can imagine top growth. The factory got more than 10,000 workers. Okay, more than 10,000 workers, and this time it happened about 50%. It means that 2 workers, one got positive. One got positive, one is positive. So that's why I estimate, say, why since last 2 days, top growth, the factory already 1,000 plus. Then yesterday even worse. So because this few days they do the swab test. Okay, so sure it will increase for especially for these 2-3 days. Because the factory, you can imagine, let's say 50%, you got more than 10,000 workers. So let's say about 12,000, 13,000. So it may go for about at least 5,000 to 6,000 workers will get positive in COVID. So that's why this few days, sure, KL area, the figure will be very high will be very high. So those who are actually studying in KL, even until early or next year, I think also difficult to go back. Okay, also still will be online, will be online. Okay, all the institutions, they will still close, all online, online, difficult. Okay, so now, okay, but all of you are actually not or nobody from KL area, from Selangor KL area. Okay, so now we continue to the example. Okay, I share the screen now. Wait, Okay, before we look at the example, okay, I provide you this one, the part 2. Okay, the example, this directly go to the example. So we look at, actually, I have provide you some, I try to reduce the size. There's some handout. Okay, these are the design chart. How to use this design chart actually? Okay, first of all, if you look at the design chart and enlarge it, the design chart, this one, FCU. FCU is the concrete cube strength. Okay, 2080 cube strength. We got grade 30, grade 35, grade 40, and so on. Okay, and this one is the beam module. Beam module, it means that here we are all based on after this 50 mm ball, based on 50 mm here, based on 50 mm beam module. It means something like this. After this, we get the 50 mm. So one way is like this. One way is we are going to estimate based on 50 mm what is the load it can sustain. Kilonewton per meter square. For example, let's say based on 50 mm, at the end you get is say 1 kilonewton per meter square. 1 kilonewton per meter square. So if your load, from your estimations, from your calculations, for the design load, there is a 6 kilonewton. So which is the 6 times of 5 of 50 mm beam module. It means that, so if it's 50 mm, it can go for 1 kilonewton per meter square. So it's 6 kilonewton. The actual load is 6 kilonewton. So you have to provide the width. If 50 times 6 means the width of the beam, the precast beam must be go up to 300. 6 times lah, 6 times. So something like this. This is one way we use like this. This is the span of the beam. Very straightforward. Okay, if the span is 7 meter, okay, the span is 7 meter, then this is the height, the h is the depth, the depth of the beam. Okay, the depth of the beam, let's say 7 meter. The depth of the beam, let's say the depth is 600. Okay, you got 400, 500, 600. So 700, 600. Then go here. You have to know what is the. This is the. Actually, this one is the. What is this? This one is the floor. Your floor. Loaded floor span. You see in the layout. You'll see from the example. Let's say is how many meter? If let's say is 7, 7 go out. You got 600, 4, 5, 6. This is 600. 7, 600. You go here. Let's say is about 6 meter. You touch here, so you can go about 2 point something kilonewton per meter square. Okay. So if your beam is 6 meter, the load is on your floor is 6 kilonewton per meter square. So it's 6 divided by this value. Then you will get what is the B, the actual B. Okay, so H, this is a H, this is a H. Okay, so never mind. We will see how to use it. So so this one is for grade 30, figure 2.21. Then 2.22, this is for C35, grade 35. This is for grade 40, all based on BIM module 50, BIM module 45, okay, 50. And this one actually, either you want to use it or don't want. Actually, this one is the for what? To get the reinforcement, AS. Once you get the size, everything, actually you can go back to what you have learned. You then say this is based on based on normal reinforced concrete, okay, normal reinforced concrete, but actually we cast in the factory, cast in the factory. So this one, to get the reinforcement, how much of reinforcement we have to calculate M over BD square, FCU, and so on. But you can go back, actually calculate the K, calculate the Z, and then can get the AS prime and the AS. But in here, it gives you more straightforward. You just calculate the M over BD square FCU directly. You can project it out, and then you can get the percentage of the reinforcement, the tension reinforcement, and percentage of the compression reinforcement required. Okay. This is a design side here. Then this is for the shear. This one is based on what BSA 110 the shear, to get the concrete shear strength, basically to get the concrete shear strength. Okay, we'll use it, see how. After this, we'll see how, okay, how to use it. Okay, yeah, basically from 2.21 until 2.25, all are the design side. Then all are design side, but it's for us to get the suitable sections, or loading, and then 2.26 actually to get the reinforcement. 2.27 is the link. Okay, it's the link for us to get the link. Okay, so I have given you this one, because in the slide it's a bit not very clear. Sometimes it's not very clear here. It's become a bit small. Okay, a bit small. So now we look at least today we can look at one example. Then coming one we can look at another 2 example. We target, actually, is it possible by 12:30 we can finish out, not drag until 1 o'clock. A bit tired. I'm quite tired here. Okay, so now let us look at it. Let us look at it. Okay, look at this example. Okay, we have a floor. Okay, we have a layout. Here is the typical layout of a precast building in figure 2, in this figure, in figure 2. And these are the data given. The data given, the design loading. Okay, you look at the floor here. Look at the floor here. Center to center of the column is 8.4 meter, is it? But however, the column, the size of the column is 400 mm square. So the actual span of the beam actually is 8 meter. Okay, if you cast a beam, actually is 8 meter, is it? Because this is 400 square, 400 square. And the spacing here, this is the one-way slab. Either the slab is a hollow core slab, 325 mm thick hollow core slab, and plus 75 mm topping. Okay, plus 75 mm topping. So your beam is go this direction, go all in this direction, and the slab is going to put in this direction. Means that support on here, left and right here. Okay, so we are going to design one of the span because it's simply supported. First of all, it's simply supported. We go for few cases. The first example for today, okay, we go for as the simply supported here. So the design loading, impose that load, the finishes is 1.2 kilonewton per meter square, okay, on the floor. Services, okay, you may have some plumbing, has some electrical fitting and so on, estimate 0.5 kilonewton per meter square. And also there is a partition, okay, there's a partition 1 kilonewton per meter square. The imposed live load, the variable actions here, QK, 5 kilonewton per meter square. And concrete, FCU, 35. Steel, the reinforcement, the higher steel, 460. Net span of precast main beam, I already mentioned net span. Here is 8 meter lah, because of the column size is, the size is what? Is 400 mm square. And the span of here, this span, the slab here is 9.6 meter. Okay, so these are the layout. So example 1, we are going to design as a full section precast beam for today lah, for today. Example 2 and 3 will go next week lah, we'll go next week. Example 1, full section precast beam and unplot construction, means that we are not going to plot it, no plotting, full sections. Okay, design the simply supported main precast beam. We design this one, we assume this one design at the center here. So you will take the slab on the left and on the right here. Okay, precast beam which are to be cast in full section. Okay, the precast beam full sections, inverted T beam lah. The beams are to be unplot during installations. Okay, no plot, means directly you will sit on the column, the connection on it. Okay, due to ceiling height. Okay, this one, due to the ceiling height, means we got the restrictions of the height of the ceiling. Okay, the floor height, the ceiling already. Overall depth of the beam should not exceed 700 mm. It means that 700 mm is the maximum depth of the beam in this example. Example number 2 is we are going to look at it. If that say without, the height is without restrictions, no limit, we can go whatever we want. Okay, not specified there. But in this example, we are going to what? Limit the depth, the maximum depth of the beam that we can go is 700 mm. Okay, 700 mm. So how are we going to do that? Let's see. Okay, something like this. We want to, first of all, we want to get the dimension actually. We want to get the dimension. So this one, the bush, the length here 150 mm actually is depending on what? On the slab, the bearing here, the connection here, the bearing of the slab that support sitting on here. Okay, so now how to get this dimension? This 150 fixed. Okay, and we have a restriction, maximum can go up to 700. Is it 700? Maximum we can go up to 700. So if 700 here, this one, the upstand here, and this one actually we are depending on what? Due to what? Due to the depth of the slab. Because the slab is mentioned here, the precast slab is 325. Okay, this is 325. So topping 75. So it's 75, 325. So it means that here is left 300 lah. Only can get 700. So we know this is 700 already. This dimension we can get it. This dimension we can get it. Now, if we want 700, what is the B, the width of this upstand? This is what we need to calculate. So in the design, actually, we are designing something like based on this size. B here multiplied by 625. The depth, effective depth lah, effective depth here. Overall depth lah, overall depth is from here to here that we're going to get to consider. Okay, step number 1, solution. We look at the solution. Step number 1 is to calculate the ultimate floor loading. Okay, we have what? Hollow core slab, 4.5. Okay, this one, how to get 4.5? 325 hollow core slab. This one you have to go from where? You have to get from the manufacturer lah. What type of hollow core slab we're going to use? I don't know whether got or not. You hold a minute, huh? I try to find out. Wait, huh? You hold a minute first, huh? I try to find out whether you can actually Google, huh? You can Google actually. One way is you Google. Wait, or I stop presenting first, huh? Wait, I try to find out. Precast design. Hume. I think I have actually like given to you before, is it? Whether I will give you or not, precast lecture notes, precast floor. Oh God, I think it's here. Yeah, it's here. So let me. Some you're not very far lah, huh? The difference, huh? I have given you last time the Humes, huh? Still remember Humes? Hume sections here, hollow core slab. Okay, if they say based on Hume here, okay, it gives you the so-called estimate the loading. Okay, 4.46, 4.46. The weight here is kilogram per meter run here, 5.04. Then you times 9.81, is it? Roughly 4.4 something, 4. So 504 times 9.81. Yeah, I think different a bit lah, So but it give you jointed weight here, KPA, give you the jointed weight here, 4.46. What you use here now in this example, in this example is 4.5 lah, 4.46 is how to get this value lah, Okay, how to get this value. So basically, this is from the catalog. If they say you may ask, you can get, if you, okay, if you work in consulting firm, especially when you work next time outside, you have actually a lot of information. Some are actually from the manufacturer, you will provide you. From the catalog, from the handbooks, you can try to find out. So it's not very far different one, okay? Not very far different. So this one, jointer weight, just how I mentioned, jointer weight is it? 4.5, 4.46 is it? So we round off 4.5 kilonewton per meter square. Topping 75 mm. It based on 20, the unit weight is 24. So 75 mm, 0.075 times 24, you get 1.8 lah, You get 1.8. Finishes 1.2. Okay, given services 0.5 and partition is 1. So the total dead load is 9 kilonewton per 9 kilonewton per 9 kilonewton per meter square. Okay, 9 kilonewton per meter square. Okay, so And then how to get the debt? Now the debt, no problem already. The debt I already just now brief it to you, because we have limited to 700. Okay, 700. This one is 150. This one also fixed because it's based on the what? Based on the requirement. Assumes that the requirement from the bearing. Okay, then you have to extend a bit. Then let's say 150 mm. 150 mm. So how to get 625? Okay, means that we minus 700 minus what? Minus the topping, 75. Okay, so and this is 325, and so we get this is 300. So the bush here, the depth is 300. Now is how are we going to get the B? How are we going to get the B? The B is the width or the width of the upstand. So when you get this one, you get the whole sections, the dimension of the whole sections. So how to do that? Now, how to do that? Okay, we have dead load 9, live load is 5. Is it? So this is based on, if based on Eurocode, is 1.35 DL times 1.5 LL or 1.35 GK plus 1.5 QK. But based on British standards here is 1.4 GK plus 1.6 QK. The factor a bit different. So 20.6. 20.6. So 20.6. Remember, look at here now. We have few parameter here. This is 9.6. Okay, and this is 8 meter. The effective span is 8 meter. So how to go? You go to the table. Go to the table. We only all based on 50 mm module. Grade 35, is it? So grade 35 is basically figure 2.22. Okay, figure 2.22. So how to start? You go from 8 meter, is it? 8 meter plus 8 meter is here, is it? And the depth is what? The depth of the beam is 625, is it? The first one is what? 400. Okay, 500, 600. So in between 600 and 700. So 8 meter, this is 4, 5, 6 here, somewhere here. 8 meter, 625. So 625, you get a point here. Then use the ruler, go here. Where? 9.6. Just now the span, the floor span, the floor span is 9.6. So go up here. Okay, go up here, then 9.6 is somewhere here. You got 8 on the right, left hand side, the vertical. Okay, 4, 5, 6, 7, 8, 9 there. You touch on it, and then you go down, you get what is 1 point something. I think 1 point something. The ultimate uniform floor load for 50 mm is 1 plus a bit. 1 plus a bit. So we have what? The load that we are calculated is 20.6. So 20.6, we just now is based on 50 mm. So now we have 20.6. So we have going to 20.6 divided by what? By the just now the ultimate load. That one is based on 50 mm module. So let's say we get a figure. Okay, 5. So is it 5? Then 5 will be times 50 mm each one. So, but this one you see is something like this. So from just now I already mentioned, from the sequence just now actually is here. A, B, C, D. You get 1.1. So you get 1.1. So 1.1 here, 1.1, we have the ultimate total load is 20.6. So 1.1 divided by 1.1 from the table, we get the value. So the N here, we require is 18.7. 18.7 multiplied by each one is 50. So it's 935. So say we go for 950. So therefore, we get the dimension. This is 950. 950. So this table, how to use this table is after this, we use this table the same way. We are going always to use the table. So class, can you get it or not? This one, before we proceed, the use of the table, understand or not? If you understand, can you comment 5? Comment 5. If you understand, please comment 5. Okay, you will comment 5. Okay. Any questions before we proceed? I just want to discuss one example. Another 2 example, we're going to do it after the midterm. We have sufficient time to do that. Okay, the rest, how is it? Not all comment. 1, 2, 3, 4, 5, 6, 7, 8. So UDL, we will just use 1.4 and 1.6 already. not UDL. That one is the factor, passive safety factor for the load for GK and QK. Last time you use 1.35, 1.5, but this one, because the table is developed based on FCU. Okay, based on FCU, so better you use 1.4, 1.6. Okay, if you've got question, it's based on what follow the example. Okay, this is the question from okay, Javin. Okay, Jovin. Okay, okay, good. Any more questions? Okay, good. Can okay, if can, then we continue we continue. So after we get the section ready, dimension settled already, now is we want to design the reinforcement. Okay, we want to design the reinforcement. This one I already explained just now because this one is not very clear. That's why I show you just now the PDF in PDF form. Okay, so the step number 3 is we already got the section ready. So the next one is we are going to design the main reinforcement and then design for the shear reinforcement. Okay, for the main reinforcement, first of all, we calculate. Now we know the dimension of the beam. We can calculate what? The weight of the beam, is it? 0.95 times 0.65, okay, is what? We are calculating because it's inverted T, is it? This is 0. Just now, this is what we use is 950, is it? 950, is it? 950. We're going to use this one, 950 for the B. Okay, so 950 multiplied by 300. Then we have also this part 150, 2 times 150 times 300, is it? Then we have also 950 times 325, is it? So this is how we get all this. Okay, or actually this one is even is easy, is 950 multiply the total depth here, you get this part, rectangular section at the middle parts. Okay, because this is 625 plus this one and this one. Okay, so we get 16.41 kilonewton per meter run for the beam. It's very huge beam. 16.41. You imagine, you see 16.41 kilonewton per meter run. It's a very huge beam. Consider because it varied the width, the width, because the depth is restricted to 700. Therefore, no choice here. We have to go wider. And mixed span, and it support the very last span of the what? Of the slab, hollow core slab, 9.6 meter. Okay, so and mixed span is 1.4 GK for the beam, plus this one 20.6. 20.6 is already calculated just now, is it? 20.6 is really factor, is it? We factor 1.4, 1.6. We factor, this is in terms of pressure, is it? On the floor, is it? So this one, 20.6 kilonewton per meter square. So this is one way, is it? Half go here, half go here. So it's 20.6 multiplied by the length here. 9.6, here half, so altogether 9.6. Therefore, you get this one. You get 20.6 times 9.6. Why? Because this 20.6 already factor. So therefore, 20.6, no need to factor again. And this one, because it's the characteristic load of the cell weight is GK, so multiply by 1.4. So this is the total W. Okay, multiply by L square over 8, is it? To get the moment. WL square over 8. L span is 8 meter. Okay, so the simply supported WL square over 8. So we get a moment 1,766 kilonewton meter. Very huge moment. You can imagine, very huge moment. 1,000 over, very large moment. And the H is okay, the effective height, the height, overall height just now 625. So minus out the concrete cover and so on. So let's say in this case, it take 515. Okay, it take 515. Effective depth is 515. So now to get the reinforcement. So in this case, actually, you can actually calculate based on rectangular section. 950 times 625. If the D is 625. Actually, you can go back to calculate the K, calculate the Z, and get the AS. But however, this one we go using the design table. It's much simpler. We can go by using the design table. Okay, design table. So design table here, how to use it? Let me show you. I show you design table. Okay, design table, is it? So you calculate the M over BD square FCU. Just now design table is figure 2.26, is it? Figure 2.26. Figure 2.26. M over BD square FCU, you can calculate. M is the moment. B is just now is B 950. D is 515. Okay, D is 515. So we calculate FCU is grade 35. So you get 0.2. You get 0.2. You get 0.2. Okay, you get the 0.2. 0.2. So how to do? You go to figure 2.26. You go figure 2.26. I go here. We go to figure 2.26. Okay. Figure 2.26. We have what? 0.2. 0.2. From here, 0.2 on the right hand side. 0.2. You go up and you touch the line here. The point here, touch the line. Then go to the left. We'll get the Pro S over FCU. Okay, Pro S over FCU 0.2. Go up, touch here. You will get about 6.3 times 10 power negative 4. Because this is times 10 power negative 4. Pro S over FCU times 10 power negative 4. So you get about 6.3. Okay, and you go further, 6.3 is it? 6.3, this is 5, 6. This is the same, 5, 6, 7. So 6.3 here, you go further here, you touch here and come down here. You get 1 point something. This one you get 1 point something for the 1.25. You say in the books here, in the notes here is given to you 1.25. 6.3, come here, come down, you get 1.25. This is for Pro S prime over FCU, which is times 10 power negative 4. Still remember in your RC design, Pro S prime here is this is for tension reinforcement. This is the percentage of the tension reinforcement. This is the percentage of the compression reinforcement required. Okay, so you get these two values, 6.3 and 1.25. All both value are times 10 power 4 negative 4. Almost finished already our we target actually. Yes, I think can before 1 we can finish. So from here we get 6.3 times 10 power 4. So Pro S how? FCU FCU 35 times 6.3 times 10 power negative 4. You must have got the calculators. Okay, this is 6.3 times 10 power negative 4 times 35, you get 0.022. Okay, 0.022. So how to get the Pro S? How to get the AS here? This is the percentage. This is the percentage. BD, this is based on BD, okay, based on BD. 0.022, is it? So the AS will be what? The AS required is 0.022 multiplied by the B 950 multiplied by the D 515. So you get 1,764. Okay, I repeat again. AS is 0.022 multiplied by B 950 and multiplied by 515. We know actually the both then ignore we just take the rectangular, that one considered effective. So in this case we provide 10T. T actually is the same as using high use steel, refer to high use steel, but 460 10T32 plus 6025 we provide 10,987, which is a bit higher than this. Okay okay, so and then go for the compression bar, because it requires compression bar. Compression, I look at that, we got the value for the compression bar, which is Pro S prime over FCU equal to 1.25 times 10 power negative 4. So Pro S prime is 1.25 times 10 power negative 4 multiplied by 35. So we get 0.0044. So AS prime is 0.0044 multiplied by B 950 multiplied by D 515. Then you get 2153. 2153. So we provide 8020 for the top bar. Actually, this is for the top. We get 2514, which is much a bit higher than AS prime. We must provide larger a bit. Okay, so you see actually like this. These are reinforcement. Just now we got provide 10T32, 6025 bottom bar, 8T20 top bar, something like this. This 8T20, 1, 2, 3, 4, 5, 6, 7, 8, 8 numbers of T20 bar. Okay, and this one we got 10T32, bottom part 10T32, and top here is 6025. Okay, 6025. This 6010 actually is the additional bar actually for additional bar for the side bar actually to hold the link actually. The purpose is to hold the link. Okay, did not show it here Did not show it here. Any question regarding on this design table to get the steel reinforcement class before we go for the link? Any question? Plus, before we go for the link, design for the link. Ada tak?
Sir.
Yes.
How do we get the 515 for the depth?
515. Oh, this one is assumed lah. Basically, if that say in the question, suppose we need to know what is the minimum concrete cover, and we have to estimate. This is similar to like what you learn in normal RC concrete. We must have the nominal concrete cover, the link, size of the link, then the reinforcement. Okay, estimate the size of the reinforcement. If they say 1 layer or 2 layer, so from there you can get the effective depth. Yui, do you get it?
Okay, thank you.
Okay. Any more questions, Plus? Any questions? If you are clear, understand. So for this, to get the reinforcement to use the design chart, it's much easy. They compare if you have to calculate the K, calculate the Z, okay? Calculate the K, calculate the Z, then get the AS. If they say your Z is greater than 0.167, if they say based on Eurocode 2, if they say based on British standard greater than 0.156, you go for compression bar is required, then you go for equation by using the compression bar, then only come back to get the tension bar. Okay, but this one straightforward. It really formate everything in the design table, actually design table. And this table, I tell you, this figure 2.27, figure 2.27 is not only used for, if this is based on British standard, in the Eurocode 2, based on Eurocode 2, they have this kind of table also. Means that when you design, you just calculate M over BD square, FCK, then you can get the reinforcement already. Okay, they have the table. We don't need to do the calculation, calculate a K, we just calculate K only lah. Then we don't need to calculate the Z and so on. The rest we can get it easily. Okay. If you are clear, please comment 6. Please comment 6. Please comment 6. Please comment 6. Okay. Okay, so now we go further to finish up this example. I think before 1 we can finish. I have to go share the screen first. I share the screen first. Okay, after we get the reinforcement, then we go for the link. We go for the link. Okay, we get for the link. Okay, this one, because it's based on BSA 110, the what to say, the design of the link actually a bit different. Design of the link a bit different. It based on compared to Eurocode 2, it's a bit different. I get a piece of paper. Wait, let me get a piece of paper first. Okay. Okay. We see first how actually in the design, the shear design of based on British standard. Maybe I have to write something. Problem here is that's why I did not bring my webcam. I have to use actually suppose to use the must easy use the what to say use a whiteboard. The concrete strength of the concrete is there is an equation. I have to write it first. 0.7 multiply by and multiply by 400. So you have a first of all, if you look at here the slide here, okay, V is the what? V is a shear force. I think this one is clear shear force 1.4 times 16.41. 16.41 is what? Because it's 16.41 is the dead load of the beam, is it? Okay, multiply by 4. Why by 4? Because it's 8 meter, is it? WL over 2, is it? To get the shear, is it? So this is due to the cell weight. 20.6. 20.6 is from here. 20.6, so 20.6, we are calculating this one. So just now is the cell weight is half go here. We simply supported, is it? So 20.6 we factor, is it? 20.6 multiply the length here become kilonewton per meter run. So multiply by 9.6. Okay. And then that one then multiply by 4. Is it? WL, is it? 4 WL over 2, is it? So 8 meter divided by 2 Okay, so therefore here you get this one. This is the maximum shear force as support, 883 kilonewton. Then after that, this is the shear stress. The shear stress. Okay, the effective shear stress, small w is W over BD. W over BD. W over BD. So W calculated BD. So we get the shear stress. The shear stress is 1.8 megapascal. 1.8 megapascal. And we are going to calculate what is the to get the shear strength. Shear strength. This is the stress apply design shear stress. So what is the strength of the concrete without the link, which is VC here, which is VC. So this VC actually there is an equation. This equation is something like this. The equation is something like this. If you refer to British standards. Okay, if you look at here, VC basically is 0.79 divided by gamma M. Gamma M is the partial safety factor material for the steel here. Okay, for shear, basically is 1.25. Okay, it's 1.25. Multiply by 100 AS over BD. 100 AS over BD. This one you see, this equation, all this I will show you and in the design for shear in the pre-stressed concrete design. I will explain it more detail actually, because the concrete shear strength, even this one actually I got, when those who are actually follow my RC design class last time, RC design 1, got follow my class, I already explained it before, I got touched it before actually. The shear strength of the concrete, reinforced concrete section without the link, what are the contribution? Okay, this 100 AS, basically is the steel bar, the main steel bar, the tension bar, extended until the end. So in this case, until the end, maybe we got do the reduction, is it? Do the curtailment. So we are not directly, we not use a full number of bar. We can simply support it. We can actually go for reduce up to 30%, left only 30%. It's not mistaken, according to the curtailment rule. Okay, 100 AS over BD, power 1 over 3, and then multiply by 400 over D. 400 over D, power 1 over 4. This D, 400 over D, if that say less than 1, we use 1. Okay, if 100 AS over BD also not greater than 3. If greater than 3, we use 3. It's not mistaken. Okay, 400 over D, if greater than 1, if less than 1, we use 1. Okay, so and then FCU over 25, power 1 over 3. FCU over 25. So the FCU, if that say less than 25, we assume it is a 25. We know the last part. If that say FCU less than 25, we use 1. The value FCU over 25, power 1 over 3, we use 1. Means assume it's using 25. Okay, but not greater than grade 40, I think. If grade more than grade 40, we use 40 megapascal. So from here, we get the concrete shear strength without the shearing. Okay, so from here, so now, okay, so here, so from here, how now we are going to use the table. Okay, wait, let me reply. I reply a message first. I reply a message first. Reply a message. WhatsApp. Ready in 25. Please include the payment for next month also, because we are in 25. Yesterday. The payment for next month also, because we are already on 25th. So I can show my friends your payment to make them pay for that. Okay, so now we are going to use the design chart. Okay, assume now in this case, assume the we got just now the main bar, the main bar that we provide here is very huge, is it? Required here is where is it? 10T32 plus 6025. But we are assumes that now the curtailment, we are not going to we are not going to what? We are not going to use all the bar extend until the end. So assume only 30%. Okay, we assume only 30% here. Okay, yeah. So assume 30%. So we calculate the Pro S FCU. So the Pro S FCU here. Pro S means that 30% Pro is a percentage, is it? So 30% Pro S just now we have calculated. How much? 0.022, is it? 0.022 multiplied by 0.3, 30%. So this value 0.022, okay, 0.022 multiplied by 0.3 multiplied by FCU 35 here. So you get 0.231. This is how you get this figure, this value 0.231. So remember, we need to calculate the Pro S FCU here, okay, and this one assume 30% of the bar of the support only use 30%, use 30%. So then we go to the figure 2.27. Go to figure 2.27, the last figure. Reduce size. Okay, so Pro S FCU is 0.23, 0.231, is it? 0.231. Okay, and now the D is 515, greater than 400. Is it? D is greater than 400. So now we based on this curve, 0.231 somewhere here. It projected out, touch here, this line greater than 400, and then go here. So this is the permissible shear stress. Actually, it's the shear strength of the concrete without the link. So it's about 0.61. Okay, in the notes it's stated here 0.61. So it's where you get the 0.61. You get 0.61. Okay, so here after this is the equations, how to get the spacing. This one, there is a problem. I don't have the whiteboard. I'm not saying I don't have the webcam. I want to show you is the difficult. They have actually three types of design. If that say V is less than or equal to 0.5 VC, no, I can say you no link lah, no link is not required. I will write, and now I write on the paper. Wait, but this one we use main beam. We still use minimum link. So this is first case. Case number 2 is I think it's I can't remember already. Greater than 0.5 VC, but less than 0.4 plus VC. Okay, so nominal or minimum or nominal link. Let's say the third case is when 0.4 plus VC is 1, but 0.8 cert FCU or 5 megapascal. We go for design link. Okay. Class, wait, hold a minute. Yeah, I think we'll hopefully we can finish before. Okay. You look at here. Is it clear or not? Can see or not? I try to enlarge my enlarge my. Okay. If you look at here, if you look at here, this one is the 3 cases. VC, you already calculated the VC, and we already also calculate the V, the shear stress, V over BD. Just now we get how much? V over BD is we get 1.8, is it? We get 1.8. Okay, VC from the table, you can based on the table just now, or you can actually use the equation 0.79 divided by gamma M 100 AS over BD 400 over D and FCU over 25. To get the VC. Then we can compare. We have the 3 cases. This is all actually stated in the core practice. We have 3 cases. In the first case, if there is say the V, the design shear stress, which is the 1.8 here, is greater or less than 0.5 VC. Okay, if based on this is based on the theory, based on the theory. 0.5 VC. Theoretically, we are not required to provide the link. Shear reinforcement is no need to provide. Okay, in this case. But however, if they say for beam, as a main beam, we're still going to provide the nominal or minimum link. Okay, this is widely used. And second case is when V, the shear stress, design shear stress, is greater than 0.5 VC, but less than 0.4 plus VC. 0.4 plus VC, how much? 0.4 plus VC, 0.61, is it just now? 0.4 plus 0.61 is 1 point something, is it? 1.01, is it? So if the design shear stress, okay, V over BD is in case number 2, then we go for nominal or minimum link. Nominal or minimum actually call the same meaning. However, in this case, actually, we are for in the third case. Third case is when the V 1.8 is greater than 0.4 plus VC, is it? But it must less than 0.8 cert FCU, 0.8 cert grade 35 or 5 megapascal, whichever is lesser. So we go for design link. We go for design link. So the equation for nominal link and design link, there's a difference. Okay, to get it, I will write some more. Okay, you wait for a moment, I write something. For nominal link or minimum, I simplify the equation. It is V equal to, because this is actually using 0.87. Actually, some are using 0.95. Depend on the edition. Let's say design link. Design link is SV is I think it's not mistaken, is this one. I think so lah. I think so. I have to check actually. I believe in my mind, in my memory is this equations. For nominal link, the SV is the 0.87 FYV. FYV is the strength of the link. Either you 250 or 460 here. ASV is the area of the link, the leg, the cross section area. You cut it how many leg, like what you design in the reinforcement in the normal reinforced concrete. Okay, divide by 0.4b. 0.4b. Then for design link, it's 0.87 FYV ASV. Okay, 0.87 or 0.95 it depends. Some version using 0.95 because we reduce the passive safety factor for the steel reinforcement. Because 0.87 is because the steel reinforcement we use 1.15. 1 over 1.15 we get 0.87. If we reduce to 1.05, it becomes 0.95. 0.87 FYV ASV. B, the bottom part B, V is the design shear stress, V over BD just now, minus the VC. Okay, so these are the equations. These are the equations we use to design. If we calculate based on not based on the table okay. However, now this is the equation. However, now we are using the table. If using the table here, you using the table, something like this. Okay, if we use the table, we use the table. We got the this one we see already done, is it? So after this, just now we go to the table. Not this one. Okay, we go to the table. Okay. Wait, let me see. Oh, not the table. Sorry, not the table. We go to the this one. Okay, once you get the VC ready, okay, you can actually substitute. Okay, SV, you see carefully the equation just now. SV is bottom part, is it? 1.8. This is, you see, SV. So if I write it, FYV is a 400. You use 460. ASV, yeah. Plus, you have to be careful. ASC, because you are using doubling. Last time we got used T10 100 or H10 100. 10 is 78.5, is it? So if T10 100, so we cut it, you got C2 leg. So 2 leg means the ASV become 157, 78.5 times 2. But now we got doubling. Doubling means here you got one link, another link. So you cut it, you will see 4 leg. So the ASV here is what? The ASV here is 4 times 78.5. So you get 314. You get 314. So then B is what? 950, is it? V is what? V is 1.8. VC is 0.61. Okay, so directly you will get this the link. What is the required link? You get so maybe you can, I show you here. You please calculate for me. What is the okay, please, if we substitute in this equation, okay, we substitute in this equation. Can you please calculate for me what is the SV? What is the SV? 100 plus, is it? Anyone can calculate and then place on the mic and tell me what is the value. 111, is it? I think it's 111, is it? 111, is it?
Yes.
Yes, 111. So you get 111 mm. So 111, then, sorry, because I did not bring the, already more than one. The form already closed. The attendance form, because I said it's 1 o'clock. You make sure you already fill out the attendance form. So from here, actually, this one is you calculate ASV over SV. then ASV is 314. ASV is 314. So at the end, you will get 111. So 111, we provide closer. We provide 100 mm. We provide 100 mm. Okay, 100 mm, and the remaining is at the both end, because higher the shear is higher at the end span, and at the middle span here we just use minimum length. We use minimum length. Minimum length is what equation? Is SV is 0.87 FYB ASV divided by 0.4B. I think you'll get 300 something, is it? So it provides 300. So this distance here, how to calculate? Is based on 2T 10 300, to get a value here, a distance. It means that 2T 10 300, it can sustain until how much of shear force? Okay, this is the distance. They got the way to calculate. We can actually got simplify, make it more conservative a bit. We can simplify based on the minimum shear stress. 0.4 plus VC. That one not say minimum shear stress. 0.4 plus VC multiplied by BD. Then to calculate the distance here, you will be a bit conservative. You'll extend a little bit. Okay, but that one I think maybe I show you next week. So at the end, we have the main reinforcement here. We got main reinforcement here. Then we got the link. The main link, actually this is the one. The first one is the main one. Second one is the link number 2. Therefore, we get 2T 10 100. This one actually we did additional link actually to basically to hold the slack of the reinforcement for the bottom part for the bush here. Okay, T10 200 here throughout along the beam. Okay, I think next week, not next week, after next week, I'm going to continue with the example 2 and 3. And example 2 and 3 will be faster because actually example 1, because we have to refer how to use the table and so on, I have to guide you first. Example 2 and 3 actually is use the same table. We're going to use it, the same table. And I will show you also how to get the distance, this one, how to get the distance. Okay, so I think today we stop here. We stop here. Any questions or not before we end out the class? This is what I target for today. At least we achieve our target. Okay, at least we achieve our target. I open for the Q&A before we end out our class. Okay or not? Already 1 o'clock. We go already take about 2 hours to discuss this subject. Any questions? If you understand, can you please comment 7? 7 comment 7. Okay. So any question? If there's no questions, if no question, then we summarize out. Today we focus on the precast beam. Okay. So precast beam, we have looked at. I have discussed to you, brief to you, explain to you some introduction. Especially you understand now the shape of the precast beam that we use available in the construction. Okay, and it depends on the type of constructions. It depends also whether it's this internal or external beam. Is it? If internal, inverted T, okay, inverted T, or it can be rectangular, also can. And the external perimeter H beam, L beam, widely used, or actually if you want to go to use the L beam is the most widely used, let's say for the side, for the H. Okay, and also whether it is composite or non-composite, depend on the construction methods. Okay, And then whether you got semi precast here is not fully precast. Semi precast, it means that part of the precast actually you will cast in situ and combine with the precast beam. So semi precast, that one also depend whether it's plot or unplot. Okay. And then after that, we are focusing the example based on the design chart. Okay, I show you the design chart. Very useful actually. I tell you, although this is the first time I teach this subject, but when I teach, I will think what is the relevance useful thing for you lah. Okay, I will try my best. Actually, I spend a lot of time actually. Spend a lot of time to read. Okay, to try to understand. I did not learn it before. Even I did not learn it before also last time. Okay, my study time. But it's not very difficult, not very tough. Okay, so we are coming class. We are going to have another 2 example. I think 2 or 3 example. And also, I see if got time, I will guide you also more like using go back to the fundamental way to do it lah. The design side, we use the design side. Good thing is what? Actually, the deflection really okay already. You no need to check. I tell you, it's no need to check. You will pass. You will pass. If you go back to the fundamental based on the fundamental equation and so on, you need to go back to check the equations. You need to check the deflection and so on. But this one you can check the deflection, no problem. They'll show you will pass. You will pass. Okay. What else? Yeah, I think roughly these are the things that we have discussed today. I hope you get something lah. You get something. And also today a bit tired because yeah, a bit tired today. A bit tired because yesterday got some events. What to say? I yesterday. Yeah, we got do some celebration at my house, a small celebration and so on, something like do some event at home. So a bit late, a bit. So if you have any question, you can ask now. If that say no questions, then we are going to end up our class for today. And I will provide you, I will give you the projects. I will give you the projects. Okay, I will prepare the project instructions and give the projects. The project basically in teams, in the groups, not more than 5%. Not more than 5%, maximum 5%. At least 3 lah. Then you all going to form your own groups. Okay, and maybe I will prepare also one Google form for you all to your grouping, so that I get your group name and group members. Who are the group members and your name of the groups of your team. And then the instructions I will pass it to, I will prepare, and then you can go and study and discuss among your group members. And after that, we meet again after the midterm. Then I may take some time to explain again, tell you what I want in the what I expect from the projects. Okay. So if no questions, so thank you very much. Okay, thank you very much. All are here. 22 students are here. So very good. The attendance very good. Just now I think also full lah. Pretty sure also full. So thank you very much. I hope that you enjoy your day. Okay. So afternoon, I know morning is very stressful for you. Okay. So you can have a rest and go for your lunch also. Or go for your lunch also. Okay. So I see you. Thank you. Bye bye.